Section 1.3.3 of Griffiths E&M, the fundamental theorem for gradients. So before we can talk about the fundamental theorem for gradients, let's just talk about the fundamental theorem of calculus, which says that if you have a function and you take the slope of that function, the derivative of that function, and you add up all of those slopes along some path, that's the integral from point A to point B, that is equivalent to taking the difference of that function at the end minus the difference of that function at the beginning. Graphically, you can think about it. If this is my function of x, and I have some path that I want to go from point A to point B, and I take little tiny steps, and I add up all of the slopes along those steps, that product, or that sum, or that integral, is the same as evaluating the function at the end point minus that function at the beginning. Okay. The same can be true, the same is true for gradients. So gradients are essentially slopes, so that shouldn't be too surprising that my total change in my function is equal to the gradient of that function dotted with dl. All right, we drew that previously. I can imagine some 3D space, or now I have some function and I take small paths. All right, now it's not just necessarily confined to a plane, but I can still take small paths. I can still take the gradient of that function along that path, and I can sum that up from beginning to end. Okay, so to do that sum, this is the contribution along one of these paths. Now the sum is just the integral. So I'll go ahead and write that I'm going to take the integral from point A to point B of my gradient of my function dotted with dl. All right, and that should be equal to my total change in my function. All right, but the total change in my function is just my function evaluated at my endpoint minus the function evaluated at the beginning. This is the fundamental theorem for gradients. So let's put that to, let's test that. Okay, this is example 1.9 in your book. We have some scalar field t is equal to x, y squared. I want to travel from the origin in the xy plane, this is A, and I want to end at point 2, 1, 2x, 1y. Now, I can figure out what the endpoints are. I can go ahead and do the beginning part first. T of my point B minus T of point A, that should be, this is, let's see, 1, let's see, 2 times 1 squared minus 0 equals 2. So the difference in those endpoints is 2. And let's take one of the paths that they define in this example. We're going to go straight from the beginning to the end. I'll leave it to you to see if you can follow the logic from along the two other paths. Okay, so a straight line from point A to point B, that has a functional form of y is equal to 1/2 x. Just like we did in a previous example, that means that dy is equal to 1/2 dx. Okay, and now if I'm going to compute the integral of my gradient dotted with my infinitesimal displacement, I need to define what that infinitesimal displacement is. And I need to calculate what the gradient is. Okay. So the gradient of this function, gradient of where is it? Xy squared is the partial with respect to x in the x-hat direction plus the partial with respect to y in the y-hat direction plus the z, but that doesn't exist in this example, of xy squared. Okay, so that is going to be y squared in the x-hat plus 2xy in the y-hat. All right, and what's my infinitesimal displacement? That is dx in the x-hat plus dy in the y-hat. But we can go ahead and rewrite, and I'll choose to do everything in terms of x's. Dx in the x-hat plus 1/2 dx in the y-hat. So I take the dot product of these two quantities, and I'm left with the integral from x equals 0 to 2 of y squared dx plus 2xy 1/2 dx. Okay, now we need to go ahead and replace the values for y. So y is equal to 1/2 x squared. That means that I go from 0 to 2. Y is 1/2 x squared, 1/2 x. That means I have 1/4 x squared. My 2's cancel, plus 1/2 x squared. I think that's right. Dx. All right. 1/4 plus 1/2 is 3/4. So I'm left with 0 to 2 of 3/4 x squared dx, which then equals 2. All right. So we've tested the fundamental theorem of gradients. We get some number 2 after we take the gradient and dot that with our infinitesimal displacement along the path that we chose, which is equal to the difference in the endpoints.